is not only sensitive to the change in resistance, but it is sensitive to the excitation also. This is the excitation. Okay, so we lose that privilege that we were getting in case of null mode of operation. When we are going, so we are getting something, we are losing something. Now I'm coming to the bridge sensitivity. Bridge sensitivity is defined as, we generally, sensitivity of any instrument we define as the change ratio of change in response to change in input or stimulus. And change in input is fractional change in resistance of the means resistance arm. Now will detection of deflection of detector in voltage sensitive bridge is given by, means if you are having any voltage sensitive detector, so obviously the deflection will be, this is SV is basically sensitivity of the voltage sensitive detector into the change in voltage across that this will lead to the response theta. So you can see that delta V we brought from here and we are putting it. So now theta is related to the change in resistance. So now we are putting, now I'm coming to the bridge. So there are two sensitivities we are dealing with here in this topic. One is your detector sensitivity. This SV is the only the detector sensitivity, means whatever detector you're putting here, voltage sensitive detector, it is sensitivity of that detector. And this is the whole bridge sensitivity. Here in this case, in the detector case, the voltage is the input and the deflection is the output. And in this case, in case of bridge, your resistance change in unknown resistance arm is input, and the theta is the output deflection in the meter. So anyway, we put this theta here, and then we are able to find the expression, bridge sensitivity expression here, you see. Now what is the advantage of what is the significance of this expression? Why did we derive this expression? What is the significance? क्यों किया हमने, क्यों derive किया इसको, क्या significance है इसका? जी बताइए, anybody?
So, we have derived this so that we can know that what maybe the sensitivity of the instrument that we must choose so as to get the better sensitivity of the bridge.
As you know that sensitivity is a attribute, is a, we always desire that sensitivity of the measurement system should be high, obviously with respect to the parameter which we want to measure. So if you are designing a Wheatstone bridge, and as you know that the sensitivity will define that means with respect to this, as far as sensitivity, significance of sensitivity is concerned, you will be able to decide how much minimum change in resistance we can measure. You understanding what I'm saying? Means you know, as a user, as a user of the Wheatstone bridge, that I want to measure this much change in resistance. So unless and until you are aware of the sensitivity of the bridge, you cannot say whether your bridge will be able to measure that much change in resistance or not. Or if you are designing your Wheatstone bridge, then and you know your requirement, how much small delta R you want to detect as per your application requirement, then you have to design and you have to implement the bridge with the sufficient sensitivity which can cater your requirement. So before implementation, You see, this expression is telling you that what are the different parameters on which your sensitivity of the bridge depends. You understanding what I'm saying? And then manipulating these values, you can um, you can calculate the sensitivity even before implementation. Means, your sensitivity of the bridge depends upon obviously the sensitivity of the detector. First of all, your sensitivity of the detector. If your detector is more sensitive, obviously your bridge will also be more sensitive. Then it also depends upon the excitation. Means you can take higher value of excitation to have a better sensitivity of the bridge. And then bridge parameters. So so you can have you can select the values of different parameters of the bridge which can enhance your sensitivity, because you are aware your bridge sensitivity depends upon what are the different parameter on which your bridge sensitivity depends. So this is what is the significance of this expression that we derived just now. Now I'm asking one question. As you know we want that our bridge sensitivity should be high. Now, for the given value of the detector sensitivity and bridge arms resistance values, we can enhance the voltage excitation to have a good sensitivity. Up to what extent can we enhance the voltage excitation? Is there any limit for that? Obviously, we want a good high value of sensitivity. That is always preferred. So what is the limitation for the excitation voltage? Or by the matter of fact, how do we decide? You are implementing a Wheatstone bridge. You took four resistances, and then you want to decide the excitation. How will you decide this excitation? जी बताइए. How will you decide this excitation?
So with the help of the rated current values of the resistance that we are using, तो मतलब हम वोल्टेज इससे ज़्यादा नहीं लगा सकते, इतना ही करंट वो कैरी कर सकते हैं. अगर वोल्टेज ज़्यादा लगाएंगे तो फिर करंट जो रेजिस्टेंस की लिमिट से ज़्यादा हो जाएगा, तो फिर वो डैमेज हो जाएंगे.
Perfect. Yes, your resistance values are means means specification of these resistances, including sensor. If you are putting sensor here, they will have their power rating also. So you have to consider their power rating also. And power rating will define the maximum current that can flow through these resistances. Suppose you must have seen carbon resistances, normal carbon resistances. They are basically quarter watt. They Carbon resistance are available in quarter watt and in the half watt also, and even, but the most common one you must have seen, they are basically quarter watt. So obviously, if this is quarter watt rating, this is quarter watt rating, this is quarter watt rating, and now the current, if current is flowing, the value of current which is flowing through these resistances, they are basically, if I square R loss is more than quarter watt, then obviously these resistances will get heated up. They won't able to handle power loss more than quarter watt. So this way, you know that you should apply the suitable voltage, so that these resistances current should be within the allowable limit, and that limit is imposed by their power rating. So your, if you are using quarter watt, so you should ensure that the current, that amount of current, only that amount of current should flow, which should not exceed the power loss of quarter watt. So this is how the excitation is decided. So everything is having its own limitation restrictions. And then obviously, we can find out what is the condition for the given value of SV sensitivity and excitation. Excitation is, as I told you, this is the criteria on the basis of which maximum excitation can be decided. With the maximum possible excitation, with the maximum available sensitivity of the detector, uh, how what is the condition for maximum bridge sensitivity? So we expanded it, simplified it a bit, and then if you look upon this expression, you'll find that when sensitivity will be high only when R by S is equal to 1, means R and S are equal. And generally we take under this we take equal arm bridge for the application. P is equal to Q is equal to R is equal to S. When this is the condition, because it is satisfying the maximum sensitivity requirement also. So the maximum value of the sensitivity, maximum value bridge sensitivity will be SV means into V upon 4, means whatever is the value of um, the uh, 1/4 of the product of your meter sensitivity, detector sensitivity, and excitation. One of the fourth will be the uh, maximum sensitivity. So this way we are able to find out, with this analysis we are able to find out the sensitivity of the bridge, and how much will be the, what is the condition of the maximum sensitivity, bridge sensitivity, and how much is the maximum sensitivity. So this analysis and these formula will be handy when you are implementing, designing and implementing a bridge. Without actually physically implementing the bridge, you can find out all the parameters. You can decide all the parameters of the bridge and you can find out whether this bridge, whatever you are designing, it will satisfy your sensitivity requirement or not. Means you can measure required delta R, means you will get the good response with respect to the required delta R. So all these things are possible. So this is this discussion, whatever I had made, it is specific to the voltage sensitive bridge, which is basically a deflection mode of operation. Now we'll come to the current sensitive bridge. Same thing we'll do for current sensitive. Whatever analysis we have done for the voltage sensitive bridge, we'll do for the current sensitive bridge. In this case, you see here we are not using a very high internal resistance meter as a detector. Here we are using galvanometer as a detector, which is basically a current sensitive. Its internal resistance is very small. So in response to the unbalance, again procedure remains same as far as the these kind of, as I told you, deflection mode is generally used when we are using the Wheatstone bridge for sensor resistance measurement. So it is um, generally it is dynamic. So in this case, initially bridge is balanced. Whatever is the initial value of the sensor, we pick up the other resistances of the bridge, and um, so that bridge is balanced. So obviously current through the galvanometer will be zero, and then if there is any change delta R in this resistance, then bridge will become unbalanced, and accordingly the amount of current will flow, and by measuring the amount of current you can measure the resistance. So this is what is done in the current sensitive bridge. So we are interested in like this here we establish a relation between delta R and the final response. Here we are interested in finding out the relation, that kind of relation between current and galvanometer current and delta R. So what we did, because we are interested in finding out the current in the detector arm, so we converted it into the Thevenin equivalent across the detector arm. We opened it, so whatever voltage that will appear here, that will be Thevenin's voltage, and then the Thevenin's equivalent resistance will be the means by looking into this terminal, whatever resistance that you will have across these terminals, and your voltage source is removed. Means removed means it is shorted. Voltage source is made zero, so we can short it. So that in under that condition, whatever resistance you will find at open circuit terminal of the detector, that will be your Thevenin's voltage, and then this is called galvanometer resistance. So this once we are able to find out this equivalent, then it is very easy to find out the galvanometer current, that E naught upon R Thevenin plus RG. So if you look upon this, when we'll make it open and try to find out E naught, it is nothing but a voltage sensitive configuration. So this will be the expression for E naught, because we are opening it. So this is the that's what I had written: V R upon R plus S minus V into P upon P plus Q. And then if there is any change in, obviously if bridge is balanced, then this difference will be zero. So if there is any change in R, that is a sensor resistance, so bridge will become unbalanced. And then we have taken the equal arm bridge PQRS. So we replace the PQ S by R, and then it is we found this expression. Finally we found this expression, then we further simplified it, and then we are able to find this expression. Now we'll make the assumption, means we'll make certain assumption based upon uh, that assumption we made here also, because delta R is very small. Generally in sensor application you will find that this delta R is very small. So this in the denominator, in comparison to the initial value of the sensor resistance, so obviously 2R will be very large in comparison to delta R. So we neglect delta R in comparison to 2R. So this is the so this is very popular expression for a bridge voltage. Later on you will find many times we'll revisit this expression. This is very popular: V upon 4 delta R upon R. Anyway, here, so we are able to find out the Thevenin equivalent voltage across the galvanometer. Now, as far as the um, Thevenin equivalent resistance is concerned, I'll try to redraw this circuit, although you may have done earlier also. The Keystone bridge, whatever means, this is your one resistance, this is your another resistance, then it is shorted, your voltage source, and then we are getting another resistance. So between these two terminals we are trying to find out the equivalent resistance. So this is P, this is Q, this is R, and this is S. So R Thevenin will be parallel combination of these two and parallel combination of these two, then these two are will be in series. So that's what I had written here: R RS upon R plus S plus PQ upon PQs, because we neglected delta R just because it is very small. So equivalent Thevenin equivalent resistance is R. So galvanometer current will be it is E naught upon R Thevenin plus G, and E naught value we are already having, so we put it here. So V into delta R upon 4R R plus G. So you look upon this expression. So in this case also you see the response. The IG is basically response of a current sensitive bridge is dependent upon delta R, that is the requirement, and it also depends upon the excitation, unlike your null mode. So by measuring IG, we can measure delta R, provided that your excitation is constant. If your your delta R is constant and your excitation is changing, then Ig will also change. So this is what I want to show you here also. In this case, you see this is the response, and this response is also dependent upon the excitation apart from the desired dependency. And then here also, they both of them are contemporary expressions. So this is what I want to show. And this expression is basically the response equation for the current sensitive Wheatstone bridge. So if anybody is having any query, any question regarding whatever I discuss about the current sensitive bridge, you can ask, please. No query. Okay. Then now our ultimate aim, objective is to find out the bridge sensitivity expression like we had in previous case. So bridge, now I'm taking the help of the voltage sensitive bridge to have expression um, for the um, means it is kind of both the circuits are duality. So in case of a voltage sensitive bridge, the deflection is equal to the sensitivity of voltage sensitive detector and into the current across the voltage sensitive detector. In case of obviously a current sensitive detector, the deflection is equal to current sensitivity of the detector into the galvanometer current through the detector. Now if we now we can write Ig is equal to delta V, E naught or delta V, because we are comparing with the voltage sensitive bridge. So E naught is equal to delta V upon R Thevenin plus Rg or G. So we can write, if we compare this expression with this expression, then we'll find that the HV is equal to SI upon. So this equivalence we have drawn, and we'll use this equivalence here. You see, because your voltage sensitive circuit and your current sensitive circuits are duality. So in case of voltage sensitive bridge, your deflection is equal to this into V into S into delta R upon R plus S. So instead of SV, we put SI upon R Thevenin plus G, that we had shown here. So here in this expression we put in terms of the current, means if your voltage sensitive detector is replaced by the corresponding current sensitive detector, then this will be the expression. And when we are taking the equal arm bridge, then R and S will be replaced by R, and finally we are able to find the simpler relation. Sorry, theta for theta, this is the relation. And then now we are coming to the bridge sensitivity, because our ultimate aim is to find out the bridge sensitivity. Then we put it here, and finally this is the bridge sensitivity of a equal arm bridge. So both of them, means here utility remains same, significance remains same, whatever we discuss in the voltage sensitive bridge. Only thing is that in this case we are using current sensitive detector, and then this is the sensitivity, uh, and all significance whatever we have discussed in the voltage sensitive bridge, it is valid for current sensitive bridge sensitivity expression also. So this is how. Uh, Now I'm going to give you one numerical example. Then you will be able to find out what is the significance of the discussion that we have made, and whatever is the outcome that we got in terms of the bridge sensitivity expression. What is the utility? Their utility will you will have good. So this is the expression. This is the example. You go through it. I want that everybody should read it one, and try to understand what is written here. Then I'll make you understand Means numerical problem is there, and that is not an issue. So we'll solve it. But uh, what is the what is the concept behind that is hidden in this problem, that I'll try to make you understand. Okay, you go through it. Also, now respond your real. Um, what do you understand by this example? Solution is also important, but I want that you try to understand what is it. कुछ बता सकते हैं इस प्रॉब्लम के बारे में? व्हाट डू यू अंडरस्टैंड बाय? जी बता सकते हैं? I just want you decipher this problem, not solution. I'm not talking about the solution. What is your understanding? देखिए, it is very simple. You have been told to design a bridge, and then bridge specifications, parameters, values are also given. Certain only thing which they are asking, means they have given even unknown resistance value also. Initial value, you can say sensor resistance initial value is given, that is 5 ohm. Then they have given you P and Q also, ratio arms, that is called value of ratio arms. Then they are saying that they are having two galvanometers having two different sensitivities, है ना? Current sensitivity, ये current sensitive bridge है, तो इसीलिए आपको current sensitive galvanometer is current sensitive वो है, तो ये आपको SI दिया हुआ है, करंट सेंसिटिविटी दी हुई है. तो आप ये पूछना चाह रहे हैं कि कौन सा ब्रिज, कौन सा galvanometer you should use in this bridge, that your bridge sensitivity should be high. मतलब out of these two, which will give you the high sensitivity. So can anybody guess? I can only say that guess at this point of time, without solving it, which out of these two galvanometer will give better um, bridge sensitivity? जी आप लोगों से पूछ रहा हूं मैं कुछ. I'm asking for
galvanometer B.
Galvanometer B. Why? Because it's
value of sensitivity is 500.
obvious. That is all. That's what I want to know. Now we'll see. We'll solve this problem, and then we'll see which out of these two will fetch us better sensitivity when we'll design. Because you know that as far as sensitivity, because we had already derived the expression for the sensitivity, bridge sensitivity. So bridge sensitivity of means this is correct, that bridge sensitivity depends upon the detector sensitivity, but it depends upon other parameters also. So means as the means if you'll see the face value, will obviously say that will, because your galvanometer B is having more current sensitivity, so obviously your bridge will also be more sensitive with it. But we'll see the significance of other parameters also, then we'll calculate. So calculation is very simple. We are already having the expressions. So first of all, we'll calculate the remaining arm resistance. So you can say that P, Q, R, S, R, whatever given in the problem, and that calculate, they are the initial values on which your bridge is balanced. So this initially bridge is balanced. Now there is a delta R. We incremented or decremented. We change this value of R by delta R. Then we'll try to find out, for that delta R, we will try to find out the sensitivity with galvanometer A and galvanometer B, sensitivity of the bridge. So you know that sensitivity of the bridge if it is for same delta R, if it is high, this is the expression for current sensitive bridge. This is the expression for theta for a current sensitive bridge. So for same sensitivity delta R, your theta will be more. So we'll find out the theta for when we are connecting for same delta R. For same delta R, we'll calculate the theta when we are connecting galvanometer A here, and when we are connecting galvanometer B here. So we'll take the ratio of it. So theta A upon theta B will be equal to, all other things will be equal. You see, only thing we are changing, bridge parameters remain same. Only thing we are changing is your galvanometer or your detector. So galvanometer related parameters will not change. Will change. Other parameter will remain same. Like in this expression, your V will be same, your S will be same, your R Thevenin will remain same, R S will remain same, R will remain same. Only G and SI will change. So in this case, you see that we are having SIA upon GA here, GA, and here we are having SIB and GB. So we took the ratio of these two, and finally we are able to find out the ratio expression for this ratio. And when we calculated it, then we are getting theta A upon theta B is equal to 1.75. Then how will you interpret it? How will you interpret it?
So galvanometer is more sensitive. 1.75
Galvanometer
times.
A is more sensitive than, not galvanometer A.
No, sir. Sorry. Actually,
Galvanometer
circuit.
A, B is, as far as galvanometer is concerned, galvanometer B is more sensitive than galvanometer A.
Yes, sir.
But when we are putting these
Circuit.
galvanometers in the bridge, then you, with less sensitive galvanometer, we are having the bridge is more sensitive with the less, because your bridge sensitivity not, it depends upon the detector sensitivity, as well as the detector internal resistance also. And because of that, because there is a huge difference in the internal resistance of the detector, galvanometer EA is, because your bridge sensitivity inversely depends upon the galvanometer resistance. So galvanometer resistance of galvanometer A is 50 ohm only, whereas for B it is 600 ohm. So despite of having high sensitivity, it is not able to give good sensitivity, higher sensitivity in comparison to galvanometer A, because of its high internal resistance. So this is what this is. I solved this problem just to show you the significance of whatever expression we have derived, sensitivity expression for the Wheatstone bridge. So now if you are having any question regarding current sensitivity, bridge sensitivity, sorry, bridge sensitivity of a current sensitive bridge, voltage sensitive bridge, and this numerical problem, if anybody is having any query, you can ask, please. You ask, please. Anybody is having any question, you can ask. Anything you are not able to understand, or you are having some doubts at certain steps, you can ask, please. Anyway, I'm assuming that you understood everything, or you're not able to understand anything. Only in these two cases, people are not able to ask any question. So, so that is my conclusion. So I'm moving ahead. So here, these topics are finished. So we were discussing about the measurement of medium resistance, and we discussed voltmeter ammeter method, substitution method, and then Wheatstone bridge. All these methods we have discussed in detail. Now the fourth method in the list was Ometer. You know? So we'll discuss Ometer now. We'll start this topic. Ohmmeter is basically a very popular way of method for measurement of resistance because it is direct reading type. It is not like your any other method where you have to make certain calculations and then you find the resistance value. Whether we are talking about the ammeter voltmeter method or substitution method or Wheatstone bridge method, this is direct reading method, and it is more popular. Although it is not very accurate, it is not as accurate as other methods, but it is basically popular because it gives the direct reading like voltmeter and ammeter. So that's why it is very popular, and it gives approximate values. It is not so there are many types of ohmmeter, and we'll discuss two main types of voltmeter, ohmmeter. One is called series type. So I had written here the ohmmeter is a direct rating device for measurement of resistance. Ohmmeter is widely employed for approximate measurement of resistance. Approximate measurement of resistance means just for the sake of general measurement, it is good. But if you are making a very like sensor resistance, if you are measuring means because you're sensing some parameter, and by measuring the resistance you are measuring the very high accuracy is required, because if you are not able to measure the resistance accurately, obviously that will transmit it to the value of that parameter which you are trying to measure. So in any case, for approximate, wherever approximate resistance measurement you require, then you can use ohmmeter. And here you don't means any person who are not technical person can also use. So we are having mainly two type of ohmmeter: series type ohmmeter and shunt type ohmmeter. Now this is a series type ohmmeter. It is very simple circuit. This is your unknown resistance. This is your unknown. These are the terminals. And then inside the instrument, these are the components. You are having a voltage source. You are having a series resistance. You are having a shunt resistance, and this is your basically permanent magnet moving coil meter. That is called mm, um, de-Arsonval movement. So now if you look very closely on this setup, then you must have studied how to convert de-Arsonval movement into the ammeter, or how can we extend the range of the permanent magnet moving coil meter ammeter. So this is the way we do. We connect a shunt across it to enhance the um, current range of the de-Arsonval movement. So this de-Arsonval movement or permanent magnet moving coil meter can be used as a voltmeter, and it can be used as an ammeter also. So depending upon how means when you will connect across it a shunt, then it will be used as a ammeter, and when you are connecting a multiplier or series resistance of the suitable value, it can be used as a voltmeter. Anyway, so I'm coming back to the ohm meter. So this you can see this is a meter, permanent magnet moving coil meter, and this is your shunt resistance. Now, now we are coming back to the measurement of unknown resistance. What will be the range of the unknown resistance? What could be the range of the unknown resistance? This resistance range, complete range I'm talking about, or extreme values.
Sir, between shunt and series resistance.
नहीं नहीं, हम तो पूछ रहे हैं कि इसकी क्या रेंज हो सकती है, मैक्सिमम रेंज क्या हो सकती है रेजिस्टेंस की, अननोन रेजिस्टेंस की रेंज या एक्सट्रीम वैल्यूज क्या हो सकती है? रेजिस्टेंस की वैल्यूज क्या हो सकती है? एक्सट्रीम वैल्यूज नहीं पता है आपको? जीरो हो सकती है, जीरो रेजिस्टेंस है।
Yes, sir.
और इन्फिनिटी हो सकती है। यही रेंज होती है, इसी के बीच में सारी वैल्यूज आएंगी। So what do you mean by zero resistance?
तो
And what
शॉर्ट
do you
सर्किट,
mean
शॉर्ट सर्किट से।
शॉर्ट सर्किट।
ओपन सर्किट
by
इन्फिनिटी के लिए।
and it is open circuit? ठीक है। Now suppose if we are shorting it, then obviously the maximum current will flow in the circuit. Am I right?
Yes, sir.
And
Yes, sir.
and this will give, meter will give you the maximum deflection, you know, full scale deflection rather. So that's why at the full scale I have written 0. And when you will make it open, when it is open, then obviously no current will flow. ओपन हो जाएगा सर्किट, सीरीज टाइप है, इसीलिए इसको सीरीज टाइप कहा गया है कि इसमें तो नो करंट विल फ्लो, एंड
Yes.
then your there will not be any deflection in the meter, so it will be, so this lower side of the scale will indicate the infinite resistance and higher side will indicate the zero resistance, and remaining value will obviously be in between these zero and infinite. So now this the shunt should be it should be designed in such a way that instrument should indicate the full scale deflection uh, at zero when resistance is zero. One means when there is a short circuit, means when you are shorting the input terminals. So we should obviously meter this. This is permanent magnet moving coil meter. So under this condition, when the input terminals are shorted, maximum current will flow. Then we should have a suitable value of shunt resistance, so that it should ensure that only in under that condition, your meter through the meter, the full rated full scale current should flow. This is the significance of shunt resistance. That's what I had written here. And obviously, if shunt resistance is not properly calculated or designed, if this shunt is not properly designed for this meter, then it may happen that under maximum current flow condition, if it is not properly designed, then this meter may the meter current may be more than whatever is the rated meter current or the full scale meter current. So under that condition, what will happen? Your meter will get damaged if meter is carrying current more than what for what it is designed for. So this shunt resistance is a very important component here. The one condition is that shunt resistance may be having a more value than the means proper value. So in that condition, if shunt resistance is more than whatever is required, then more current will flow through the meter and it may damage your meter. And or shunt resistance may be less than. In that case, obviously, when under short circuit condition, when your input terminals are shorted, then if shunt resistance is less than is the proper value or required value, then full scale deflection under maximum current condition, you won't get the full scale deflection. So both of these situations, although in other case, when less amount of current is flowing through the meter, your meter is perfectly safe. There is no issue as far as the meter safety is concerned. But it will reduce its sensitivity, because this scale is indicating the resistance. This scale of the permanent magnet moving coil meter is indicating the resistance in the ohm meter. So if we are connecting a larger value means if in the case of maximum current condition, if it is not giving full scale deflection, then your sensitivity of the meter is compromised. It means it will be less. So both the conditions are not desirable. Both the conditions are not desirable. You are understanding what I'm saying?
Yes, sir.
We have to have this proper value of shunt resistance. It should what kind of shunt resistance we should have? We should have shunt resistance when suitable value of resistance that should ensure that under maximum current condition your meter should give you full scale deflection. It should not give means the current that amount of current should flow that should ensure the full scale deflection, and under that condition it should not more amount of current should not go through the meter for which it is designed, and less amount of current should also not flow. So accordingly we have to design the shunt resistance in such a way. So this is what is the point. Now, whatever I had discussed that is given here, when a terminal A and B is left open, no current flows through the meter and there will no deflection, and no deflection position of pointer corresponds to the open circuit resistance. A convenient quantity used in design of the ohm meter is Rx is equal to. In ohm meter design, this is one of the design specification that we should know, that when Rx is equal to RH, it is RH is the resistance at which your meter should give half scale deflection. That's what it is told, because range is having no meaning here, because your highest value is the infinite, that is. So generally you'll find half scale deflection values are given. This defines the range, that half scale deflection is this much. So that's what it is told, which if Rx is equal to RH, this resistance causes the half scale deflection of ohmmeter when connected across it. Now these are the parameters that you are required to have. These are the specification, you should have with you. Only then you will be able to design the um, ohmmeter, series type ohmmeter we are talking. तो आप जो मीटर यूज कर रहे हैं, whatever permanent magnet moving coil diagonal wall movement, you should know the range of full scale deflection current, means rated current. So we should design shunt in such a way that maximum current, when maximum current is flowing in the circuit, obviously it will be short circuit current, means when the terminals are short circuit. Under this condition, meter should carry, your meter current should be equal to, IM should be equal to IFM, full scale meter current. ठीक है, बात समझ में आ रही है? ठीक है. सो आपको ये मालूम होना चाहिए, जाहिर बात है आप इंप्लीमेंट करने जा रहे हैं, डिजाइन करने जा रहे हैं, देन यू शुड नो that what is the full scale deflection of the meter, current of the meter, then internal resistance of the permanent moving coil meter. These two are the specification of your meter, whatever meter that you will employ to implement or to design your series type ohmmeter. Then you should know the battery voltage, and then you should draw how much current you will draw from the battery when IFM flows through the meter, means in maximum current condition. And you know what is the maximum current condition when these input terminals are shorted. So these parameters are the design specifications parameter that will be known. Only then you will be able to design the. So our objective in design of series type ohmmeter is that calculate the value of RSC and RSS such that meter should not produce over or under deflection for our given design specification. Means our meter should not give over over deflection or under deflection under the maximum current condition. Under the maximum current. Yes. Somebody is asking something. Oh, sorry. I'm sorry. So we'll discuss this on the next turn. I'm stopping my deliberation here, and we'll discuss it on the next.